This is lecture 22 on urban transportation planning. We will continue our discussion on trip distribution analysis in this lecture. Before we continue our discussion, let us recollect briefly what we did in the previous class. You may recall we discussed about the general formulation of the gravity model of trip distribution and then apply the gravity model for a given situation involving 3 traffic zones, and the friction factor values for a movement between the traffic zones were also given to us. With that information, we just understood that for this particular case, since only 3 traffic zones are involved and Kij zone to zone adjustment factor is given as 1, we wrote the gravity model in this form. Tijk was written as Pi Ajk Fij divided by sigma j equal to 1 to 3, only 3 traffic zones, Ajk Fij, right. Using this formulation, we found Tij values for k is equal to 1, first iteration. We have just completed one iteration, and the result of the first iteration is this. This is the result we got in the previous class. The cell values of the matrix is nothing but the trip distribution between zonal pairs, right, and we found that the sum of the cell values along each row works out to the corresponding total trip productions of the zones, whereas when you sum up the cell values along columns, they are not giving values corresponding to the total trip attraction by the traffic zones. That is a problem. In addition, please note that when you add the cell values along a row, you are not exactly getting the whole number that we have written in the last row. They are not adding up to exactly 14, exactly 33 and exactly 28.00. If you add up, it may end up with some fractional number which is very close to the whole number indicated in the column, right. When you are rounding off the values to the higher whole number, or if you are leaving out the decimal part when it is less than 0.5, you will be getting these numbers as 14, 33 and 28, right. And if you look at the trip attraction values, we are getting 37.03 against a given value of 33 in the original problem, and we get a value of 23.59 against a given value of 28 in the problem, and we are getting a value of 14.37 instead of 14. Trip attraction values given to us for zones 2, 3 as well as 1 are 33, 28 and 14, similar to the numbers, but the zone numbers are different when you compare productions and attractions. Okay. Now, our aim should be to see that the sum of the cell values along each column also works out to the actual given trip attraction values. For that purpose, we this is what we discussed now, there is no need to repeat again, and we discussed about some correction procedure to calculate an attraction value which can be used for the subsequent iteration. And Ajk is the adjusted attraction for iteration k, Aj is the desired attraction which is known to us for the base year condition, right, and Aj k minus 1, as we can guess, is the adjusted attraction pertaining to iteration k minus 1, the previous iteration, right. And of course Cj k minus 1 is calculated attraction for iteration k minus 1. So that is how we just formulate this adjustment procedure. You can see here, if you use this adjustment procedure, you will find that if your calculated attraction value is very high, this procedure will result in a reducing effect, and if your calculated value is very low, then this procedure will help to increase the value. Cj k minus 1 is in the denominator, okay, which is the calculated value of attraction. We will see with the numerical example how this correction procedure works. For the second iteration k is equal to 2, the adjusted attraction values can be calculated using the previous formulation like this. I have again listed the values of Aj as 33, 28 and 14. These are the actual desired attraction values. Cj2 minus 1, or in this case Cj1, which we get after the completion of first iteration, is 37.03, 23.59 and 14.37, right. And the value of attraction which was given as input for the iteration that was just completed is Aj2 minus 1, isn't it, that is Aj1. In this case Aj1 happens to be Aj itself because it is first iteration, isn't it. That is how Aj1 is also given as 33, 28 and 14. Then use the correction formula, get the value of attraction Aj2 for second iteration, and that is obtained as 29.41, right, 33.23 and 13.64. Check what has happened to the previous value. We have got a calculated value of 37.03 as trip attraction for zone 1, which is much higher than the desired value of 33. This has to be reduced, okay. By using this correction procedure, we get a value of 29.41 as attraction value for zone 1, which will be given as input to the subsequent iteration, and we are going to check whether we are able to get the desired result or not. And similarly, we have got a value of 23.59 as Aj2 instead of 28, a lesser value. The correction procedure has given us a high value. So when you put in this higher value, probably there is scope for increasing the value of Aj2. That is how the correction procedure works. Here instead of 14 we have got 14.37. So we are going to input a value of only 13.64 because still we want to reduce this to 14, okay. And with these attraction values we will be repeating the calculations to get the value of Tij for each of the zonal pairs, clear. Now let us work out T11, and it works out to 1.46. the only difference is the Aj values are different in this case, isn't it. T12 10.40, T13 using the same procedure 2.14. Then trips from zone 2, T21 works out to 16.93, T22 works out to 9.95 and T23 is 6.12. And for zone 3, T31 15.28, T32 6.91 T33 5.81. Now we are ready with the values to be filled in the matrix to check whether we are able to get the desired attraction values. Let us present the result in the form of a matrix as shown here. As usual, when you add up the cell values along rows, we are getting the actual observed production values of 14, 33 and 28. You can check for every iteration, you will be getting it, right. And if you look at the attraction values, now the values are little better than what it was in the first iteration. We get 33.67 instead of 33, 27.26 instead of 28 and 14.07 instead of 14, right. Now the question is where to stop or when to stop the iterative procedure. Are you happy with these values? Now if you logically round off even the attraction values, 33.67 can be rounded off to only 34. Ultimately we have to round off all these numbers including each cell value to a whole number, then only your trip distribution matrix is valid, logical. You cannot have fractions in your final result, right. When you try to round off 27.26, we end up with 27, they are not matching with the desired values. So that is how you must have a feel of the need for continuing your iterative process. So there is no need for iterative process if by rounding up procedure you are able to get the desired numbers, whereas here it is not so, so we need to continue our iteration. Third iteration, the adjusted attraction values are to be calculated first, and the calculation is similar to what we have done earlier. Now we can see interestingly the value of A1 that we got at the end of second iteration was 29.41, right. The value given as input for second iteration was 33.67 and the desired value is 33. So when you do this adjustment we end up with 28.82. We are going to give an input which is much less than the desired value, right, and we will check whether we are able to come closer to the desired value of 33, right. And in the next case you can see AJ2 after second iteration had been 33.23 and the input was 27.26 and now we are going to give an input of 34.13, right. And for AJ3 it is going to be 13.57 against the input value of 14.07, okay. With these AJ values let us proceed with the third iteration. The process will be continued with the new values of attraction, in this case AJ3 till a satisfactory agreement is reached between the desired and predicted values of attraction, that is our target. So let us go ahead with the calculation of T11 as 1.4, T12 10.47, T13 2.08, T21 is 16.64, T22 10.24, T23 6.11, 31 15.06, T32 7.13, T33 5.81. This completes the third iteration. Let us put the result in the form of a matrix and check whether we have achieved the desired result. This is the result. I am showing you simultaneously the desired values also. First, let us try to check the attraction numbers. We have got 33.1, which can be rounded off to 33. 27.84 can be rounded off to 28, and 14.00 exactly we are getting, so we accept the number, right. Also, please check the logic of rounding off of all the cell values starting from 1 1, 1.4 rounded off to 1, 10.47 rounded off to 11, 47 becomes 0.5, then it becomes 11, and 2.08 gets rounded off to 2. And please note, in reality you may have number of cell values, about 100 in a row. When you do this rounding off business, simply rounding off to a higher number if the fraction is more than 0.5, and rounding off to lower number when it is less than 0.5. The second decimal place or third places may have some effect. In such a case, in 1 or 2 cells you may have to make a compromise, okay, which should not affect your overall result, right. So, that is to be kept in mind. Okay. In a certain case, some 10.49 may have to be rounded off to only 10 to get adjusted with the overall requirement. Okay. So, that is the reality. And in second row, if you look at 16.64 rounded off to 17, 10.24 to 10, 6.11 to 6, right, 15.06 to 15, 7.13 to 7, 5.81 to 6, and the totals are totaling up to exact production values of 14, 33 and 28, and if you add up the cell values along each column, you get exactly the desired values of attractions of 33, 28 and 14. Even though it is iterative, we find that it is possible to achieve the desired result with repeated working with the gravity model with the input of the adjustment procedure, right. This is how we work with this gravity model. Next we will see how to really calibrate the gravity model. You may recall, in this problem the Fij values were given to us, right. We got the Fij values in the form of a matrix and those values were substituted, but in reality Fij values will not be known to us. You may have base year trip distribution data. Using that data, we should be able to work out the Fij value for zonal pairs, and that should be used in the gravity model for actually distributing the trips or getting the Tij values. So, we have to check or try to understand how to go about getting the value of Fij to be used in the gravity model formulation. And this procedure is what we call as calibration of a gravity model. Just to recollect the general form of the gravity model, this is the general formulation. Tij is Pi Aj Fij divided by sigma j is equal to 1 to n Aj Fij. Our interest here is to get the value of Fij. Fij is the friction factor which represents the travel impedance between zones, isn't it? That is how we have understood Fij, and you may recall originally it was 1 by Wij raised to power c, and for our convenience we have just taken that factor as Fij, right. It is inverse of a function of travel impedance between traffic zones. This impedance can be explained using travel time, travel cost, travel comfort, okay, travel safety, all together as a bundle, all transformed into equivalent money value. That is how we understand Wij, clear. And calibration is a process of estimating the parameters of trip distribution model such that the model best fits the observed data. Now the question is, what exactly is the parameter that we are going to estimate? The process of calibrating a gravity model depends on the assumed mathematical function of the friction factor Fij. Initially we have taken Fij as 1 by Wij raised to power c. Wij is a bundle of several factors related to the modes of transportation, including foot, bicycle, IPT, public transit, motorized personal vehicles and so on. But normally we do trip distribution by segmenting data based on mode used for travel. We also discussed about this in the previous class. Why should we segment data based on mode used for travel? Any response? Can we not put the data set pertaining to all the modes of travel together and do trip distribution? You may recall I gave the example of trips made by foot. Distribution of trips made by foot will be confined to a set of few zones. If you consider one zone, maybe the adjoining zones may be involved in trips made by foot. If you consider trips made by bicycle, distances may be slightly more. With motorized modes of transportation, the spread of trips will be covering a wider land space, isn't it? So obviously there is reason to segment the data based on mode used for travel for the purpose of trip distribution. Once you segment the data based on mode used for travel, then travel time is going to be same, because only one mode we are talking about, isn't it? Average travel time by a mode is going to be same. Travel cost is going to be same, will be remaining constant. Comfort, safety, all these factors will be almost constant terms, right. So if your distribution is mode based, you can consider travel time as a sole basis to assess the frictional resistance for movement between zones. You may wonder, why not travel distance, why travel time? You have to answer this question. Why not take travel distance as the basis? Why should we take travel time? Yes, travel distance can replicate the effect of travel time provided the transport infrastructure in the form of the way, the vehicle, the control and the terminals are same throughout the network in which the particular mode is used. In practice it may not be so. On a route, a stretch of 2 kilometers may have very narrow road, another stretch may be having wider road, right. This trip may involve a length of 5 kilometers. There may be another route with very wide road throughout, the trip length may be about 6.5 kilometers between the same origin and destination. and if you compare the travel time, the time by the longer route, relatively longer route, may be less compared to the time through the shorter route. And as urban travelers, we are concerned about travel time, how fast I can reach a destination by a particular mode, and the travel resistance felt is normally in terms of time rather than distance, isn't it? So that is how it is always taken as time and not distance because of these problems. Okay. This implies that it is possible to give Fij as a function of travel time, right. The popular functional forms are these. Fij is given as Tij raised to power some parameter beta. It could be beta, A, B or C, whatever, right, and this form is called polynomial form or power function of Fij. And Fij can also be expressed in negative exponential form, e power minus beta times Tij. Also we can express Fij using two parameters, Tij raised to power alpha and then e power minus beta times Tij. You may wonder why so many functional forms. It depends upon the actual travel pattern, right. So each city may have its own transport system and the road network. So the effect of frictional resistance will be explained in different forms depending upon the field condition. That is why they are given different alternative forms, even though in most cases the polynomial form might suit, but there are other alternatives available, so that depending upon the need you can try the other functional forms too. There is one more form, simple discontinuous function, recommended by BPR, Bureau of Public Roads USA. This is nothing but a combination of these functional forms based on the trip length expressed in the form of travel time. You can choose a function for trips from 0 to 2 kilometers, then for trips from 2 to 4 kilometers you can have another functional form, right. They encourage discontinuous functions, whereas in the other cases once you fix a functional form, irrespective of the travel distance it is going to be same, right. They felt it may not work well for all trip lengths, it is better to have discontinuous function with different functional forms depending upon the length of travel involved. That was recommended by the Bureau of Public Roads. Okay. And let us just have a feel or the graphical form of these functions, so that you can have a feel of the variation of Fij over travel time or travel distance, mostly travel time. Let us take travel time in x axis and the Fij value in y axis. Okay. And if you take the first one, polynomial function, this will be the variation of Fij value. Generally Fij will decrease with increase in travel time, okay. And the other function, negative exponential, will have this shape, similar trend, but slope will be steep at the initial values of Tij, and then it will be almost similar to the previous one. This is a 2 parameter function which will increase initially, reach a maximum and then decrease subsequently. And the BPR method will result in this kind of curve, broken curves. That means each piece will have a different functional form. Parameter value will be different for different stretches. Okay. So, the slope of these bits of lines vary depending upon the travel time range in which it is falling. Clear? So, this is how the friction factor has to be determined. You may wonder, why not take Tij itself as Fij? Why should we express Fij as a function of Tij? Can you answer this question? Why not simply take Tij as Fij? Why expressing Fij as function of Tij? Because in practice it is found that distribution cannot be explained by travel time alone. It has to be a function. That is the only reality is that. So, these are all empirical suggestions made based on the field observations, right. You cannot explain trip distribution simply using directly the travel time between zonal pairs. You need to express it in the form of some function of Tij. Clear? And this is the general shape of frequency distribution curves for the commonly used functional forms of travel resistance or travel impedance between zones. Now, with this understanding, let us look into the details of calibration procedure as recommended by the Bureau of Public Roads, which is most commonly adopted as of now, because of the reason that assuming a single functional form for any travel time is not working well in practice. So, there is a need to have different functional forms based on the travel time implication. That is why BPR method is used in most cases. The procedure aims at establishing a relationship between the friction factor Fij and the unit of spatial separation Tij for a chosen set of trip lengths, As I indicated earlier, chosen set could be 0 to 2 kilometers, 2 to 5 kilometers, 5 to 10, 10 to 15, 15 to 20, 20 to 25 and so on. That is how you need to understand the chosen set of trip lengths. Kilometers are the corresponding travel times, right. So, 3 minutes of travel time, 3 to 6 minutes, 6 to 10 minutes, 10 to 20, 20 to 30 and so on, right. This function is then used along with the constraints of attraction and production to get the values of trip distribution. Constraints of production and attraction we have discussed about. So, we need to see that the Pi and Aj values match finally, and we do this iteratively. Then trip length frequency distribution curves. Trip length frequency distribution curves using the observed and calculated values of trip interchanges are drawn. What do you understand by trip length frequency distribution curves? Or how do you understand trip length frequency? Let us hold the curves for the time being. What do you understand by trip length frequency? Let us say we are segmenting trip based on travel time as trips from 0 to 5 minutes, 5 to 10 minutes, 10 to 15 minutes, 15, 20, 20, 30, 30, 40 and so on. Okay. That is the segmented trip length. What is frequency? Number of trips falling over that trip length segment is frequency, isn't it? Right? Frequency is nothing but the number of observations pertaining to a particular identified condition, isn't it? We are fixing the travel time range 0 to 5 minutes. Over the entire urban area, you can find out how many trips are falling in this particular travel time range. Is it possible or not? You have the data for the base year condition. We would have collected data about the trips made by households, right, between traffic zones, and the travel time involved. Everything will be known to us, mode used, the information is with us. So with that pool of data, it is possible to pick out the trips pertaining to this range, travel time falling between 0 to 5 minutes, right. Total number we can get, right, and that number is nothing but the frequency corresponding to that particular range of travel time or particular range of trip length, clear. And when you plot relating the number of trips falling in each of the range and the ranges, you get trip length frequency distribution curves, clear. Now, so you draw the curves, and if the calibration is correct, the observed and simulated or calculated using gravity model, isn't it? Trip length frequency distribution curves should be close to each other. We have the observed values of trip length frequency. Then we are going to distribute the trips using gravity model. After distribution, you can get the numbers corresponding to each of the trip lengths, because for each trip length you are going to have a different function. So you will have the total number of trips, right. On the same set of axes you make both the plots, one pertaining to the observed values, the other one pertaining to the model simulated or the values that you obtain using the gravity model, right. And if your assumed functional form for the friction factor is correct, right, then the curve pertaining to model value will be very close to the observed, the curve pertaining to the observed values, or almost matching with the curve pertaining to the actual field observed values. When this criterion is not met, because if they are not matching with one another, a new set of friction factors may be estimated. If they are not matching, the reason is obvious. Our friction factor assumption is not accurate, it is not really replicating the field observed trip distribution pattern. Change your functional form, okay, get a new Fij value and then distribute the trips using gravity model with that Fij value, right. Please note here a new set of friction factors. Set means set pertaining to each travel time block, okay. We are going to change and then redo the whole exercise. And once you get the calculated as well as field observed values, you should do some modification for the second iteration. That iterative procedure has to follow this correction procedure as we did in the case of correction for adjustment values, not adjustment, attraction values in the case of trip distribution, right. Here F dash is a friction factor for a given travel time to be used in the next iteration. We finished one iteration, made the plot pertaining to gravity model as well as the observed data, found that the curves are not matching satisfactorily. We are now proceeding with the second iteration, okay, with this correction procedure. F is a friction factor used in the calibration just completed. OD% is the percentage of total trips occurring for a given travel time observed in the travel survey. This is observed trip length frequency expressed in the form of percentage of the total. OD% is nothing but observed percentage of the frequency pertaining to a particular trip length, and GM% is a gravity model percentage you get from your gravity model application, the percentage of total trips occurring for a given travel time simulated by the gravity model. Clear? So, get a new friction factor value and apply that, okay, for the second iteration and continue the process. The procedure is repeated until the calculated and observed trip length frequency distribution curves match with each other to a satisfactory extent, right. This is the trip length frequency distribution curve. Trip length very rarely taken as kilometer. If everything is same over the entire network, then probably you can accept travel distance. If the vehicle, control system, terminal, everything is same over the whole network, then there may not be much of variation. You can take either distance or time, but mostly it is time. To make that point clear, I have put both kilometer as well as minute, okay, for trip length. And the percentage of trips made is given along y axis. Please note, this is the range of trips falling over one trip length segment. It could be 0 to 5 minutes, right. And let us say we observe certain number of trips falling in this time range, and where do we fix that number in the graph? That number corresponds to this point. This point is at the middle of this range, because it is a representative number for the entire range. It should not pertain to the dividing lines here on x axis. It should be at the middle of the range, right. Similarly, the number of trips observed to be falling the range of trip length of 5 to 10 minutes should be plotted midway between these 2 points here. That is how you get connection between these 2 points, and the curve is plotted like this. That is the point to be remembered carefully, not exactly to the end points, it is to the mid values. Clear? And you see here the observed value is given by unbroken line and calculated frequency broken line. There is some match. This is just an example given, and it is up to the planner to decide whether to proceed further with the iterative procedure or stop at a particular stage. It is physical verification of matching of the 2 curves, okay. But with the experience you can easily understand that understand or fix the stage at which you will be able to stop the iterative procedure. If you continue with that procedure in any iterative process, you may have a point of convergence and then divergence. If you go on iterating, you will find that you will reach a point of convergence. If you continue further, the error may increase, the overall cumulative error may increase. From that you can fix the point of convergence and stop your iterative procedure. Do you agree with this statement or not? If you do the iterative process, in any case you will touch a point of convergence, and if you continue further there will be divergence again. So you will be able to fix the point at which you will be you have to stop, okay, that is possible. The final phase of the Bureau of Public Roads calibration procedure is to calculate the zone to zone adjustment factor Kij. You may recall we talked about Kij. Kij has to be used where there are some special effects which makes the trip attraction or trip distribution between zonal pairs to be totally different from the normal value of trip distribution. Okay. Examples I have given you earlier, a public sector undertaking fixing a factory in one zone and putting all the employees in another zone, and if you look at the distribution of trips, large number of trips will be distributed between this particular zonal pair. So this may not be matching with the normal pattern of trip distribution that you observe for the whole of the urban area. So to explain this only, we talked about zone to zone adjustment factor to take care of the variation in the socio-economic characteristics or the connectivity between zonal pairs based on socio-economic characteristics. The procedure recommended by BPR is this: you can calculate Kij to be Rij multiplied by 1 minus xi whole divided by 1 minus xi Rij, and Kij is the adjustment factor to be applied to movements between zones I and j. This implies that Kij will have different values for different zonal pairs, right. K12 will be different from K13, K14 and so on, right. Rij is the ratio of Tij based on OD survey or observed, you can say Tij OD survey divided by Tij gravity model. Are you able to appreciate the logic of getting the ratio Rij as the ratio of observed trip interchanges and model estimated trip interchanges between a zonal pair? We do this because of variation between the observed value of Tij and model simulated value of Tij. Obviously both are to be brought together to do some correction and get some correction factor in the form of Kij. And xi, another interesting factor, is equal to the ratio of Tij observed divided by Pi observed again, the production value, trip production value of zone I, okay. And Tij as we observed in the field from I to other zones. Or you may wonder, why should we have the production value here in this equation? The only explanation is that BPR has obtained this formulation based on number of field studies conducted in the US. They have done lot of iterations involving all the involved variables and finally found that this is the best way of accounting for special connectivity between zonal pairs because of socio-economic factors which are different from the normally observed connections between zonal pairs. Okay. You can take this as an empirical formulation pertaining to the US condition because it has been recommended by BPR. And of course, we can try this formulation for our conditions, and probably it is a interesting research problem, and if some of you are interested, you can check whether the Kij recommended by BPR can be applied for Indian condition. If not, what is the modification to be brought into to suit our situation, right. We will stop here to summarize what we have seen so far. We were at the middle of doing a numerical example in the application of gravity model when we started the class. We understood the iterative procedure involved in the application of gravity model, and we also appreciated the way the trip attraction values are adjusted at each iteration level, and finally the possibility of getting the right expected value of trip interchanges in the matrix. And we also found that it is also possible to get the whole numbers which are more logical for all the cells in the matrix, which resulted in the whole numbers for trip attraction values also, right. Then we discussed about the calibration procedure for the gravity model. This basically implies getting some value for Fij in the gravity model, and there are different possibilities of getting the value of Fij. The normal procedure is expressing Fij as a function of travel time, because distribution is normally done based on mode used for travel, and there are different possible functional forms, and we have to choose an appropriate functional form depending upon the data available as well as other field conditions. But BPR, Bureau of Public Roads USA, has recommended a different approach. They have recommended different functional forms based on trip length expressed in terms of the travel time, and the BPR calibration procedure is an iterative procedure providing for modification of the friction factor value if the observed trip length frequency distribution curve and the model simulated trip length frequency distribution curves are not matching. And BPR has also recommended a formula which is empirical to get the value of zone to zone adjustment factor, namely Kij. So with this we will stop for today and continue with the rest of it in the next class.